present an overview of the Franciscus project, which standing name is Fracture Mechanics Testing or Irradiated RPV Steels by means of SUb-sized Specimens. Activity that has been prepared with my colleagues Sergio Cicero, Borja Arroyo, and Sergio, Arrieta. The contents of the presentation will consist of the motivation to start this project, an introduction of the key aspects, the research project together with the project status, and the contribution that the University of Cantabria is going to do to the project, and finally the conclusions. Okay, as you all know, one of the main issues we're facing right now in Europe is the energy crisis. In this sense, the long-term operation of the nuclear power plants seems to be an attractive option because it's the less expensive energy to be produced. Besides, together with the renewable energy, it may help to achieve the energy transition goal proposed by the European Union by 2050. So, if we pretend to extend the safe operation of the nuclear power plants, one of the most important things to do is ensure the structural integrity of the reactor pressure vessels. This huge component is really important for several reasons. It's the primary barrier against the release of irradiation into the environment. Its failure is excluded in normal or accidental scenarios by design. It cannot be replaced, or at least it's really difficult, and it suffers from thermal aging and irradiation exposure. In this sense, the nuclear power plants have implemented this surveillance program, which consists in removing some specimens from the surveillance capsules that, of course, are inside the RPV to be tested time to time. So, once the results of these tests are obtained, the treatment of the RPV can be measured by mainly two approaches. The first one is based on charming techniques, that is the most common, mainly for historical reasons, no? And the second one is the master curve approach. That this well-known approach allows us to determine, no, the fracture toughness within the ductile to brittle transition zone. So, in this sense, the Lerner methodology, the master curve, is more interesting for us because by just knowing a single parameter, the reference temperature, we can obtain the fracture toughness for any temperature. In both methodologies, the irradiation can be quantified as the shift between the unirradiated curve and the irradiated one. The important thing here is that in order to perform this test, you need, of course, material, and the current nuclear power plants are running out of material. So, in this sense, a new proposal was introduced by using the miniature compact testing specimen with the master curve approach. This specimen that you can see in the figure have the dimensions. The other ones are 10 millimeters per 9.6 millimeters for 4 millimeters of thickness. This is the standard specimen proposed by Franciscus, but of course some of the partners are using slightly taller specimens. This specimen is small enough to machine up to a mini CT specimen for a one broken shark. This idea has been already validated, for example, on Miura in 2010. He obtained a reference temperature for with the mini CT specimen that was in good agreement with larger specimens. So, this mini CT specimen brings us a series of advantages. For example, you can reuse a broken specimen to machine these small ones. You reduce the volume of irradiated material, which is very important. You can increase the surveillance database with direct measure of fracture toughness. And in case of material inhomogeneity, you can characterize the local properties, the material local properties. So, encouraged by these advantages, these promising previous results, a new project named Fractisus began in October of 2020. Thanks to the European funding, and it will last for 4 years. This project has been structured in 7 work packages, of which we, Mr. Cantabria, are leaders of the work package 6, the dissemination, training and education and data management, and the coordinator of the project is the SEK CERN. In this project, 22 laboratories are participating, 19 from Europe, 1 from Japan, 1 from Canada, and 1 from the United States. The main objectives of this project is to demonstrate the real ability to use the mini-SID specimen to measure the fractal toughness in RPV materials, to demonstrate applicability to use these specimens in combination with the master curve approach to characterize the material within the tactile to brittle transition zone, and establish the foundations of the mini-SIDs for use the mini-SID specimens in future codes and standards. With all this, following the technology readiness levels proposed by the European Commission, we can assume that right now we are in the level 5, and thanks to the Fractisus effort, we are going to move to the level 7. So, meaning that the mini-SID specimen will be validated and demonstrated in real operational environment. So, the first and one of the most crucial tasks in this project was accomplished, and is the material selection, being all of 10 of great relevance for the nuclear industry. Some of them you can check in the sheet. We have base materials, weld materials. The material properties of this dataset are representative of a large number of RPV materials. These materials have different chemical composition, treatments, and of course we can train this material in both baseline and irradiated conditions. Also, this dataset covers a large range of reference temperatures. Currently, we are working in the round robin test, which consists in one material to be tested by several participants. For unirradiated materials, we are performing 6 round robins, in which are participants 3, 4, or 5 laboratories, while for irradiated material, we are performing just 1 round robin, but in this case, 7 participants are involved. By doing this, we pretend to detect gaps or technical difficulties between laboratories, and of course, we pretend to expand the material database. Just here mention that this activity is going to be finished in a few weeks, so an open report will be released if you wish to check it. Okay. The University of Cantabria is contributing in 2 other round robins. In this case, for the AMP5 material, A533 material. Additionally, we are going to perform, while going to characterize a common structural steel, for example, the 275, with mini-SID specimens and with a small punch test, in order to extend this methodology beyond nuclear materials. All these tests will be analyzed by fractography, and finally we will carry out some evaluation, and we will perform some recommendations and guidelines. Of course, another important task of our work is the dissemination, training, and data management. In this sense, we are participating in several conferences, writing some dissemination papers, and following the European Commission recommendation, all the data generated by Fractisus will be open in the repositories you can check here. So I encourage you, of course, to use the data as you wish. Summing up, some conclusion. The mini-SID specimens provide a wide range of possibilities and advantages. Fractisus must overcome some uncertainties for acceptance of mini-SID specimens by the local authorities. The initial phase was focused on the material selection, crucial for the project progress, and the first results from the round robin tests are being obtained. And that's all from my side. Thank you very much for your attention.
Marcos. So we are open for questions now. Yes, please.
So are the small CT toughness results going to be compared with big CT toughness results to assess constraint effects?
Yeah, it's that in the internet. Yeah. The MCT is going to be compared with a larger specimen. Yeah.
And are you just going to test one size of big CT and one size of small CT? Or are you going to do
In general, all the material we have selected has been fully characterized yet in other projects. So yeah, we have the fracture toughness, we have fracturography from other projects. Yeah.
And have you seen any differences in like size effects between the two so far?
Right now, we have not yet completed that comparison. It's something we are going to do in the future. Yeah.
Further questions, please? Marcos, I have one question.
Okay.
Concerning because one set of specimens will be in the presence of radiation, is that correct? You said that you have a bench of tests that will be carried out. What are the sort of, I imagine it's a difficult test to carry out. The facilities and protection and everything should be quite appropriate. So, can you speak a little bit about this, the difficulties involved?
Okay. In our laboratory, we have not hot cells to do the irradiated test, so I cannot much about this topic. But of course,
but do you put the radiation during the test or before the test? You expose the material to the radiation before the test, then you take it to the lab and do it?
Are they decommissioned parts or are they irradiated?
Yeah.
Are the materials off the plant? That's the prior irradiated material. They've been taken out of the cells. So they have levels of fluence in them already. Irradiation. Or are you going to use?
No, if I'm correct, these materials are being irradiated. I mean, it's not after the test, before the test.
Or the surveillance cell samples that goes into the surveillance tubes and are extracted.
Yeah. But of course, in the research art.
Okay.
Right. Any other question? No, so thank you. We can move to the second one.